Okay, so for this part of the lesson, what we will do is we will talk about that is known as the Le Chatelier principle, which is dealing with what is happening with the system in equilibrium when you introduce a change to the system. So we said on the first part of it that when we have that is known as the dynamic equilibrium, whatever at the same rate that the forward reaction is happening, the reverse reaction is happening as well. The balance, of course, is a very, very delicate, and it's very, we have to keep in mind it's very careful. So if a change is introduced, then the balance will shift to a new equilibrium position, so that more or less of the desired product is formed, or the reactant is formed. When we say, let's clear this first. When we say that the reaction is shifted to the right, let's say, what is happening at that case? We mean that the net reaction, this is the same as saying that net reaction is from left to right. So from the reactant toward the product. Okay, there are several variables that we will take into the consideration in terms of the stress or the changes that we are implementing to the system in equilibrium. And those are changes in concentration, changes in temperature, changes in pressure and volume. Okay, so let's talk about the Le Chatelier principle. As you guess, he's French. The Le Chatelier principle, for simplicity, we are calling it LCP. So every time that we say LCP, we means the Chatelier principle. So it's saying, the Chatelier principle is saying, if an external stress which means stress means that something that you are a new thing that you are introducing to the system is applied to a system in equilibrium. The system will adjust. The system will adjust in such a way so that the stress is reversed, is cancelled. The stress is offset. And the system reaches a new equilibrium position. Again, as I said here, the word stress means that you are introducing a change in pressure, volume, concentration, or temperature. Okay, so those are like a lot of words here. However, In other words, in very simple words, you will say, for this Le Chatelier principle, is whatever you do, the system will react to cancel it. So whatever you do to equilibrium system, the system will react to cancel it, to undo it. So let's say that you are adding heat. You are adding heat, increasing the temperature. Then what the system will do will react in a way to use that heat. React on the way to use that heat. If you are increasing the concentration, what the system will do will react so that is the concentration that you are increasing is decreased. Is decreased. If you are increasing logic, if you are increasing pressure, the system will react to reduce the pressure. Okay, so let's take it one by one. Let's suppose that we have this as the reaction. Nitrogen gas and hydrogen gas are combined together to form okay. So let's suppose now that we have a system at a certain temperature at 750 degrees Celsius. The equilibrium constant is 2.37 times 10 to the power of -3. And in the certain experiment, the equilibrium constant is whatever is given. So the equilibrium constant for nitrogen gas is 0.683. The concentration of hydrogen gas is 8.80 molarity, and the concentration of NH3 is 1.05 molarity. Now, let's suppose that what we are doing is we are adding NH3 so that the concentration, adding NH3 so that the concentration of NH3 is now 3.65 molarity. Let's use now this principle and see what is happening here. Okay, so the stress that is applied, or the change that is introduced to the system in equilibrium, implemented, is the increase of concentration of NH3. Okay? The react of the system to this change will be what? Will be to decrease it. The concentration of NH3. How is it going to decrease the concentration of NH3? By going on the other direction, by decomposing NH3 in N2 and H2. Okay? So then, what will happen if we write this reaction? You increase the concentration of this, then the reaction moves on this direction. So the power now goes to the left. The reaction is shifted to the left, which means that NH3 is decomposed in nitrogen and hydrogen gas. Make sense? So let's see the first thing, that is the effect of changes in temperature. So let's suppose that we have an endothermic reaction. An endothermic reaction in a general form will be expressed something like this. A plus B plus heat will give us C and D. So now what is happening is we are increasing the stress that we are introducing, the change that we are introducing to the system in equilibrium. So this is a system in equilibrium. This is important to keep in mind, okay? It's a system in equilibrium. Now, what we are doing is we are increasing the heat. So this is the stress that we are implementing to the system in equilibrium. If we increase the heat based on LCP, it is saying that we'll do whatever it takes to cancel, to use up the change that we are doing. So if we are increasing the heat will do whatever it takes to use up that heat. So therefore, the system, the equilibrium will be shifted to the right of the reaction. So we'll use up the heat that we are changing, that we are making that we are stressing the equilibrium system to reach a new equilibrium system. Okay? So if we increase the temperature, the system will try to use up the heat. How is it using it up? By taking that to the other side of the equilibrium. So then this is why it is what we will see is we will see that more C and D and D are established, are present than A and B, because the system is moving toward the product side of the reaction. Okay, so now let's suppose that what you are doing is you are decreasing now. Okay, you are decreasing the heat. So will be A plus B plus heat, and in equilibrium is C plus D. Now what you are doing is you are decreasing the heat. So the system being in equilibrium will say, oh, no, don't decrease the heat. I will do whatever it takes to increase the heat. And in order to increase the heat, what does it have to be? It has to move or to be shifted to the left. This is what shifted to the left means. So what you will see on that case, you will see more A and B than C and D present. Okay? So if the temperature is decreased, the equilibrium will shift toward the side with a heat term. Okay, so it doesn't matter, increase or decrease. Okay, so when temperature is increased, the shift will be away from the side with the heat term. We'll want to use this. And when temperature is decreased, the shift will be toward the side that the heat term is. Heat. Toward the side of the heat term. Okay, so this is the logical. Now we'll see some examples on it. So let's take a look now. Let's suppose that we have A in gas plus B in gas plus 32.5 kilojoules will give us C in gas and D in gases. Okay, so now if we'll use the color coded here, if the heat is increased or the temperature is increased, so when the temperature is increased, then the heat is, which this is an endothermic reaction, okay, and the heat now is on the left side of the reaction. So what will happen is that the system will try to use the heat that was stressed, was added to the system. Okay, so the system being in equilibrium, it is added something new, then we'll try to use that whatever is introduced to, is stressed to, so the system will go to the right. So the equilibrium will shift. The equilibrium will shift to the right. However, if the temperature is decreased now, see what will happen on that case. the temperature is decreased, then what will happen is the system will say, no, 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 I want the same thing. So I will try to undo what you did to me. I will try to cancel whatever you did to me. You decrease the heat by decreasing the temperature. Therefore, I will try to produce more. So the reaction will be shifted, equilibrium will shift to the left. Okay. However, if you have now an exothermic reaction, okay, if you have something like this, X gases plus Y gases is giving you W gases. And then delta heat is negative, I don't know, 83 kilojoules. Now, what do you see here is that the heat of the reaction is written outside the reaction. The very first step will be to have the heat, or the heat of reaction as part of the reaction. So let's rewrite this as a thermochemical reaction. So this will be X gases plus Y gases will give us W plus gases plus 83 kilojoules. And so now, again, we'll use the same. When it's increasing is red, when it is decreasing is blue. So when you increase the heat, okay, what the system is saying that, no, I don't want it to be increased. I will do whatever it takes to cancel out what you did. So the system will move to the left. Okay, so when temperature is increased, but now we have an exothermic reaction. When the temperature is increased, then the system will shift to the left. Okay, and now let's see what is happening when the heat is decreased. So if the heat is decreased, then the system will be like, I will cancel whatever you are doing. So in order to cancel whatever you are doing is I need to produce more heat. So then what will happen is in an exothermic, when temperature is decreased, then the shift will be to the right. Okay? This is temperature. Let's see concentration. So let's suppose that we have this reaction. H2 plus I2, and we're reaching the equilibrium at 2HI. Okay, so now what I do, I disturb the system, the equilibrium system, by adding H2. Then what the system is saying that, no, I don't want this to happen. In order to not to react to the change, then it will want to use up the H2, okay? And the system will shift to the right, okay? So this will be, well, right here, to the right, okay? Now, what I do is I say that, no, okay, I will decrease the concentration of the H2. Then what the system will do is will say, no, you should not make those changes. You should not introduce those changes to me. I will undo what you have done by producing more to increase the concentration. Okay, so those two are connected together, and those two are connected together. Okay, now let's rewrite this again and then see what is happening when you change the concentration of I2. So you increase the concentration of iodine. Then what is happening? The system is saying, no, I want to undo what you did by producing more HI. Okay? And then you're saying, okay, I will do another change. I will decrease the concentration of I2. Then what the system will say is that, no, I don't want this to happen. So what I will do is I will increase the production of I2. Okay? Now, let's take a look at the last part of it. So we have H2 gas plus I2 to HI. So now, what I'm saying is that I'm increasing the concentration of HI. And then what the system is saying, no, I don't want this to happen. So I will use up what you increased. And how do you use it up? By going on the other direction, shifting to the left. And then if you decrease the concentration of HI, then the system again is undoing what you did by producing more. So that the concentration is what you are doing is undone. Now, we say, so everything that is here, those arrows here going to the left or going to the right, we say that the shift is happening to the left or to the right. So on this example here, when we were increasing the concentration of hydrogen gas, then the reaction was, or the equilibrium was shifted to the right. When you decrease the concentration of hydrogen, then the equilibrium is shifted to the left. When you increase the concentration of iodine, the equilibrium is shifted to the right. Okay, and when you decrease the concentration of iodine, then the equilibrium is shifted to the left. And here, when we increase the concentration of HI, the equilibrium is shifted to the left. And when we decrease the concentration of HI, the equilibrium is shifted to the left. I hope that this makes sense, and we'll do more examples like this in class as well. So now to summarize, if the concentration of the substance in an equilibrium is increased, so concentration of a substance is increased, if a substance in an equilibrium is increased, the equilibrium will shift toward the other side of the equation. if it is increased, okay? So that it is reacting to consume, let's say, to eat up the increase that you are doing. And if the equilibrium is decreased, if the concentration of a substance in equilibrium is decreased, then will shift toward the side that the substance is, toward the side to produce more, the substance that you are decreasing the concentration. Okay, so let's suppose that you have this PCl5, PCl3, and chlorine. So let's take now, if the concentration of PCl5 is increased, so if the concentration is increased, then the system will be saying, no, I don't want this, we'll use it up and will be shifted to the right. Okay, if the concentration of PLCA5 is decreased, then will be shifted to the left. Will produce more, okay? And if the concentration of PCl3 is increased, the system will be shifted to the gas. So you increase this, the system will be shifted to produce more to the left. And if the PCl3 concentration is decreased, the shift will happen to the right. Same thing will happen for chlorine as it is to the PCl3. Okay, so let's take a look now to the effect of change in pressure. So there are several things that we have to keep in mind here. Pressure and the volume are inverse proportion of each other. So pressure and volume are inverse proportion of each other. What does that mean? Is that if you increase the pressure, I will use a different color. If you increase the pressure, the volume will be decreased. Think about it, if you have a piston with like a mechanism that you change the volume of it, a cylinder with that you have a movable piston on it, then when you increase the pressure, then you decrease the volume. And if you decrease the pressure, then you increase the volume. So they are direct proportion of each other. So more moles of gas in a certain volume, the higher the pressure. Okay, let's write this down. More moles when we are balancing the reaction and we see that in one side there are more moles of gas in a certain volume, means higher pressure. Higher pressure. Okay, so if the total pressure of the system at equilibrium is increased, the equilibrium will shift toward the side with less moles of gas. So if the total pressure of a system in equilibrium is increased, then the shift will happen will be toward the one with the less number of moles. So let's suppose that we have this nitrogen gas plus hydrogen gas will give you NH3 gas. Okay, so now this will be 3. In this side of the reaction, what do we have? 1 plus 3, 4 moles of gas. Okay, and on this side of the reaction, we have 2 moles of gas. Keep in mind what is happening with pressure and volume, that they are inverse proportional of each other. So whatever we are saying for pressure now will be the opposite for volume. Okay, makes sense? So we said here that if the total pressure is increased, so if pressure is increased, then we'll go toward the less number of moles. So less number of moles will be into NH3, correct? So now when we have the introducing to the change of volume for the same reaction, NH3, what do we have to keep in mind is just the fact that volume and pressure are opposite of each other, inverse proportion of each other. So if the total volume of the container is increased, so volume is increased, this means that is the same as saying pressure is decreased, okay? Because they are inverse proportional of each other. If volume is increased, pressure is decreased. And now the shift, therefore, the shift will be to the side with more moles. Be toward more moles, which in this case, when we have the system in equilibrium, more moles is to the reactant. So it will be to the left. And if volume is decreased, that means is the same thing to say that pressure is increased. Therefore, the shift will go toward less moles. Okay, which is a shift in our case to the right. Okay. Okay, so now let's emphasize something here. Because we have talked about two concepts, is the rate and the shift. So they are related to each other, but they are not exactly the same thing. So when we have a reaction, let's say X plus Y plus heat, which is an endothermic, will give you Z. Then if you increase the temperature, which means you increase the heat, the shift will happen to use up that heat, will go to the right, and the rate will increase. Okay? And if you decrease the heat, then the direction in which the power of the reaction will be is to the left, and the rate will decrease. The rate of reaction will decrease, which means that only the change in temperature changes the value of the equilibrium constant. The change on concentration, pressure, volume, for as long as you are keeping it at the same temperature, the equilibrium constant do not change. So equilibrium constant will change only when you change, you stress, we'll say, stress the system in equilibrium. Regarding heat. We will have a new equilibrium system when the heat is stressed into the system in equilibrium. The equilibrium constants will not change when the pressure, volume, and concentration are implemented, let's say, to the system in equilibrium. Okay? Even a catalyst can speed up the process, but it has no effect on the equilibrium constant or in the equilibrium concentration of the reacting species. Okay? So keep this in mind, that the shift will happen on all the cases. The heat, pressure, volume, concentrations are stressed. However, for pressure, volume, and concentration, the constant equilibrium constant will stay the same, and for heat will change. This is it.